Hello and welcome back to yet another video in this Hadoop series. This is video 2.0 and the prerequisite actually is video 1. So the video 1 was pretty simple about explaining what is Hadoop in a very basic way for like a wider set of audience. But this video is aimed for those audience who want to understand what exactly goes into the Hadoop. What are the components of Hadoop? So let's get started with this introduction. So in this video, pretty much we're going to see what are the basic building blocks which make up Hadoop. So there are like 4 basic building blocks which make up Hadoop, which is the name node, the secondary name node, the job tracker, the task tracker, and data nodes. So I would recommend you to memorize these 4 words or 4 or 5 words: the name node, secondary name node, job tracker, task tracker, and data node. And in the subsequent slides as we go forward, I would be explaining what each of these are and what do they do. So let's get started. As I explained, like Hadoop is like an operating system like environment which is sitting on a distributed computing cluster. So in this case, say you have a 100 node cluster. In the right hand side of this slide, I'm showing you those 100 nodes, but since I don't have the space to show the 100 nodes, I'm just representing them by 6 nodes. When I say node, it basically means a computer. And the left hand side, I have like 3 nodes or 3 different computers which operate in master mode. They are namely the name node, the secondary name node, and the job tracker. The name node, the secondary name node, and job trackers are like servers with some kind of software configurations and software installed in them. And these 3 nodes run in master mode: the name node, job tracker, and secondary name node. Each one of them is a separate server, a hardware machine with some software installed on it for some specific purpose, which we shall discuss as we go forward. And in the right hand side are those nodes which basically are the computers which belong to your cluster, which are called as data nodes. Each data node is basically a computer. Say it would have its dedicated CPUs, dedicated memory, that's a RAM, and a dedicated hard drive. And the task trackers are software daemons which is continuously running and monitoring the data nodes. So, but all of these computers are actually connected. All of these computers, the data nodes, the name node, secondary name node, and the job tracker, all of them are actually internetworked. So the Wi-Fi router on top here pretty much implies that all these computers are connected in a cluster. So the computers on the left hand side, the name node, secondary name node, and job tracker, they run in master mode. And the computers on the right hand side, the data nodes, the task tracker, these are actually the slave nodes. I repeat once again, like if you have a 100 node cluster, these data nodes would actually form those 100 nodes. When I say a node, it basically means a computer or a computing resource. So pretty much that's it with this slide. So going forward, we're going to in detail try to understand what exactly are the roles and responsibilities of the name node, why is it sitting there, and what is this guy, the big brainy guy with huge eyeballs popping out, the busy guy, the busy looking guy over there, the job tracker does, and what does the secondary name node do, and what are these data nodes and the task tracker do together. So going forward, now recalling the discussion in the previous video, the video 1, where I discussed about a 1 GB input file being split into 2 different halves and given to 2 different computers. That was the beginning or the basic understanding of parallel processing, like the same problem which is being solved by multiple computers to save some time. Not just some time, but a lot of time. Now, let's take for an example, we have a 200 MB input file. Let's assume that the name of the input file is going to be N, the letter N or the alphabet N. And this file is a text file which is filled with numbers separated by space. And the numbers are, for example, like 100 space, 200 followed by space, and 237 followed by space, and 67, and so on. So when this file actually is sent into the Hadoop cluster, what would happen? And meanwhile, the data nodes in the right hand side, this region, the DN1, DN2, DN3, DN4, are the host names of the data nodes. The guy over here, the guy sitting in front of the computer, doesn't imply that there needs to be an operator looking into the computer and monitoring tasks. No, the guy over here in the picture depicts a task tracker, which is basically a software which is monitoring the data node. And every data node, as I explained, is a dedicated machine. It has its own CPU, it has its own memory, that's a RAM, and it has its own hard drive. The big blue cylindrical disk over here, the stack of disks, these actually represent the hard drive on each data node, and each data node has its own host name. So, what would happen to this input file when it is submitted to the Hadoop cluster? The cluster, the Hadoop cluster, by default, or the Hadoop framework, I would say the Hadoop framework by default, would divide this input file into blocks of size 64 MB. And mind you, the size of 64 MB can be reconfigured by the user, by the programmer, to also be 128 MB. For certain reasons, it's just optimized to be 64 MB and 128 MB, which we will discuss later. Alright, so you have the input file of size 200 MB, which is being divided into 4 input splits, and each of these blocks would now be treated as a separate file. It's an individual and independent file. The names of these individual files would be N1, N2, N3, N4. The last file is just occupying 8 MB. The next obvious question is, where would these files be stored? On which of these files would be stored on which of the data node? Since Hadoop is all about distributed computing, Hadoop also has a file system which is distributed. Like a file would not be residing on a single machine as a single file. Instead, the file would be split across in smaller chunks of 64 MB size, and then it would be distributed across the cluster. So this is distributed computing and distributed storage and distributed retrieval. So the file system which actually enables you to do this actually is HDFS. So HDFS is a file system component, the Hadoop distributed file system component, which enables the splitting up of these files and ensuring that these files is distributed across the cluster for like load sharing. Now, say N1, the block N1 or the file N1 is sent to data node 1, N2 is sent to data node 10, N3 is sent to data node 6, and N4 is sent to data node 7. So who decides which block of the original file has to go to which particular data node? This decision actually is taken by the file system manager. The decision is taken by the Hadoop distributed file system manager. It has its own set of algorithms which takes care of like how to locate or how to place the files and how to read the files. So you don't have to worry too much about like what is the algorithm, what goes into the decision making of which block goes to which particular data node. So you don't have to worry about that. For time being, you can just understand that there is a file system manager, which is the HDFS manager, the Hadoop distributed file system manager, which takes care of deciding which file block goes and resides on which data node. It's not done randomly. So remember, it's not done randomly at all. Going forward, like who splits the data blocks, I pretty much told it's going to be the file system manager, the Hadoop distribution file system manager. It's not the name node, it's not the secondary name node which does the operation of splitting the files. It's a file system manager which splits the file. So going forward, now what happens if data node 10 fails? Now the original file N was 200 MB in size. It's now got split into 4 chunks of 64 MB each, and each of those block is treated as a separate file, and it's going to get stored on a separate data node. Now what if one of the data nodes containing the file block fails? It's like the original file data is now no longer valid. So what do? We need to ensure that we have multiple copies of these blocks, which is called as replicating the data. So there is something called as replication factor, or it's a configurable number which decides how many copies of the input blocks I need to maintain across the cluster. It's a configurable number by default. In Hadoop, it's set to 3. It can also be set to 5 on a per file basis. For the sake of discussion in this example, we shall actually consider that to be, like 2, replication factor of 2. So 2 copies of every block would be present across the cluster. Going forward, if we have our replication factor set to 2, you would see N1, there's one copy here with data node 1, and N1, there's another copy with data node 3. Similarly, N2, there's another copy with, there's one copy with data node 4, and one copy with data node 10. And N3, there is one copy here, and another copy here, and N4 is going to be with data node 12 and data node 7, pretty much. Okay, now what if data node 12 goes down? What if data node 12 goes down? Immediately, a trigger message will be sent by the data node to the HDFS file system manager, or the Hadoop distributed file system manager. Hey, the replication factor for N4 is now going to be equal to 1. So what the HDFS manager, the file system manager, would do is like, it would make sure somebody else is copying, some other data node actually is copying the N4 block from data node 7 to ensure that the replication factor is always 2 across the cluster. So if somebody goes down now, say for example, if data node 12 goes down, a trigger message would be sent to the file system manager to ensure that another copy of N4 is made by using the copy of N4 present in data node 7. So eventually the replication factor of 2 for every block will be maintained across the cluster. So going forward, now we shall actually discuss about what exactly is a basic functionality of name node without getting into the implementation level details and what exactly does a secondary name node do. So you don't have to get confused between the previous slide and this slide. The previous slide has 6 different data nodes, and this slide is just having 6 different, the previous slide had 12 data nodes, and this slide is going to have just 6 data nodes. Don't get confused between that and this. This 6 data nodes is just because of the space constraints in the slide. I'm just trying to fit as many data nodes as possible in the slide. So don't get confused where the 6 data nodes go. It's there, but I'm not able to show it over here. So this picture over here in the right hand side, this diagram in the right hand side of the slide pretty much shows 6 data nodes having a replication factor of 2 for the file blocks residing on them. So N1 has 2 copies, and N2, there are 2 copies of N2, and N3, 1 over here and 1 over here, and N4, 2 copies. So replication factor of 2, for the sake of this discussion, is now actually satisfied here. Now let's try to understand what exactly is a name node. What exactly is the role of the name node? As I told you, name node is a dedicated hardware server with some software installed on it, and it is designed to do a particular task. What is the task of name node? The name node basically is like a file system server. It's like the master directory which knows where exactly the file blocks are residing. So the file blocks, when we say file blocks, it would have various attributes like what is the original parent file name, how many input blocks, how many file splits does the original block have, and what is the replication factor, what is the size of each block, on which data node are each of these blocks residing. All this information is going to be present in the name node. So if you actually want to locate a file, name node is the guy whom you want to go to, because this guy has a snapshot of the entire file distribution in the cluster which is maintained by Hadoop. So name node is like a file system directory server. It knows where the files are and how many blocks the original files are split into, what is the replication factor for the file, where exactly those blocks are residing. So all this information is present with a name node. Now what does a secondary name node do? Secondary name node pretty much takes a backup of this file system server contents. Basically, secondary name node backs up all the content from name node. So in the event of failure of a name node, the contents of the secondary name node will have to be now physically copied to the name node, and then the name node has to be fixed and restarted. So the secondary name node is just like a backup server for the name node. And remember, the secondary name node in Hadoop 1.0 doesn't work in hot standby mode. Hot standby mode meaning like it doesn't work like a tandem backup server. It doesn't actually come up immediately in the event of a name node failure. When the name node fails, it means that the whole cluster goes down, because you will no longer be able to locate where the files are located, or files are residing on the data nodes. So if name node goes down, we have to copy the files from the secondary name node, and then we have to restart the name node after fixing it. So secondary name node is like an office assistant. It just like assists the name node by keeping a backup of all the contents what is present in the name node. Going forward, having a basic understanding of what exactly are the basic components of Hadoop. Now, why did we have Hadoop in place? Because it's like a software manager for a distributed computing needs. So when we have a distributed computing cluster in place, we need to actually submit a job. Recall the first video in which we submitted an input file of say 1 GB in size, and that file was actually filled up with numbers, and we actually manually split the file and gave it to two different computers which had a software installed to process the file and give you the sum of all the numbers to whatever input file it's processing. So we need to get some kind of a job done by your Hadoop cluster, which is basically a data intensive processing job. Now when we say a job, what exactly is a job in a Hadoop ecosystem? A job is basically a task. It's basically a program which you want to execute, or it can be a collection of programs which you want to execute on an input file. So a job is usually some task which is submitted by the user to the Hadoop cluster. When we say a job, it has to obviously be a program or a collection of programs or compiled binaries. So when we say a job in the Hadoop environment, it's actually called as a MapReduce job. MapReduce is one of the kinds of jobs in Hadoop. So it's written in Java. So the programs are written in Java. So when you compile them and you compress them, it actually becomes a jar file. So for the people from non-Java background, a non-Java programming background, can just think of it like a collection of compiled binaries. That's it, or a collection of programs, to be even more simple. So a job is basically a collection of programs, or a single program which is designed to operate or do some kind of processing on an input, and the input is basically going to be a file which would be already residing in the Hadoop cluster, and then eventually there must be a place for the program to throw out all the output of the operation. So basically the attributes of a job include a program or a collection of programs, an input file or a set of input files stored in a directory, and an output directory where the output of the computation is going to be sent. So having spoken about a job, let's discuss about how to submit a job and execute a job in the Hadoop ecosystem. The diagram over here in the right hand side, which actually shows a series of racks where the data nodes could be loaded. So this is a typical a deployment scenario in a lab where the Hadoop cluster is set up, and this is a rack. You can see a series of racks over here, and each of these racks can easily have like 20 or more data nodes. So 1, 2, 3, 4, 5, 6, approximately more than 100 data nodes. Like, oh my god, I forgot these things. If you add up all these things, it comes up to close to a 1,000 node cluster. So this diagram over here, these are all data nodes, and these data nodes are actually working in the slave mode, if you recall back from the first slide. And then you have the master nodes, the job tracker, the secondary name node, and the name node. These are the nodes which work in the master mode, which control many kinds of operations and tasks which is happening on these slave data nodes. Now, how do we actually, having spoken about a job, how do we submit a job? How do we submit a job, which is basically a set of programs, and get them executed on a Hadoop cluster? So imagine you're an employee. You would obviously be an employee of an organization, and you've just figured out that your organization has a Hadoop cluster, and you have a task at hand which is like data intensive processing. So you need to submit the task to the Hadoop cluster. So you have your laptop or your desktop, which is not a part of the Hadoop cluster, but you will have to install some softwares on it and configure your system in such a way that it can communicate with the Hadoop cluster, but it's not a part of the Hadoop cluster. So yours is actually a client machine. So this guy sitting in the left is pretty much you, who is an engineer in your organization, who would be submitting Hadoop jobs to the cluster, for which you need to have some software installed and your system configured to be able to talk to the Hadoop cluster. So one of that software actually is called as the job client. The job client would be installed on your system, which enables you to actually talk to the Hadoop cluster. So once the user jobs are submitted, it would go from job client, and eventually the name node, the job tracker, is actually going to pitch in and take up the job processing, which we would see in the next slide how exactly a job gets executed in a Hadoop cluster. Now, having said that, you have submitted a job from your client machine having the software which is called as a job client into this Hadoop cluster. Now what happens is, I'm just showing the data nodes as four data nodes because of the space constraint. I'm not able to accommodate more data nodes. They ideally represent like hundreds or thousands of data nodes. So when a user submits a job to the client machine, the job client would accept the job and it's picked up by the job tracker. The job tracker again is a separate machine. It's a dedicated hardware, a very powerful machine with some special software configurations on it, which does the following thing. So a job basically contains a jar file, which is a collection of programs, collection of Java programs, and a job would also have an input directory, an output directory from where the input files are picked up and to where the output of computation will have to be finally stored. The job tracker identifies those task trackers where the job can actually be run. Now remember, in traditional model of computing, we brought the data to the program, but in this distributed computing, we are taking the program and executing it wherever the input file splits are loaded. So if you have the original file filled with numbers of 200 MB size divided into 4 input splits, the program, if your program is submitted to add up the numbers in each file, those programs will be exactly run on those data nodes which is having those file splits located. So the job tracker's basic functionality is to identify those data nodes where the input file corresponding to the job is located and make a copy of all those jar files and make sure that they are run. So once all these data nodes actually finish their computation, the results will be aggregated and sent back to the user. So how that happens, we shall discuss it in MapReduce and not now. For time being, just have a high level understanding that the input file is going to be split into multiple blocks of 64 MB chunks and stored in a distributed environment with the help of HDFS Manager, which is the Hadoop Distributed File System Manager. And when you submit a job, the job will definitely contain an input file or a path to an input file and a program to operate or a set of programs to operate on the input file and output directory. The job will be picked up by the job tracker. The job tracker's task is to schedule those jobs, identify which of those data nodes actually have the corresponding input file which is related to the job, and make sure the job or the program gets run in all of those data nodes in a distributed fashion. What do those task trackers do? The task trackers basically monitors the progress of the jobs submitted to the data nodes. So data nodes will be running a lot of programs, and task trackers' responsibility is to ensure that all of those jobs runs to completion. And once they run to completion, it should be notified to the job tracker. Then job tracker again takes over to ensure that something else is done on those output files. Basically, it has to be combined to get the final output. So the job tracker does a lot of operations after the task trackers finish the execution of the program. There are good chances that a job need not run to completion. There could be several reasons why a job could fail. A job could be killed. So in the event of a job failure, it is the responsibility of the task tracker, which is a software daemon which keeps running on each data node, which keeps monitoring whatever is happening on the data node. It needs to report it back to the job tracker. So the job tracker decides what needs to be done next. So that's it. So you can just go through the points here to summarize everything. Now, the final slide is about putting everything together. In the Hadoop ecosystem, we spoke about the Hadoop distributed file system, the HDFS, the name node, the secondary name node, the job tracker, the data nodes, and each data node is monitored by a task tracker. These things, 1, 2, 3, these four, the sandwich of these four items in the middle of this actually forms the core of Hadoop, or basically the main components, the major components of Hadoop. And when I spoke about each of these, when I say name node, it's a dedicated hardware and it has a software running on it. Those software which actually enables the functionalities of the name node run on a Java virtual machine. They run on a JVM. I'm not going to get into the details of explaining what exactly a JVM is, but they run on a JVM, and the JVM runs on a native operating system, and by default the Hadoop supports Linux. So it's run on a Linux based operating system. So the JVM would be running on a Linux based operating system, and every of the software which basically makes up the name node, the secondary name node, the job tracker, all of them would be running on a separate JVM. So this is pretty much how it's organized. And then in the left hand side, this blue box speaks about a set of tools, which is nothing but data integration tools and data mining tools. When I say about data integration tools, the whole idea of Hadoop actually is to do some kind of intensive data processing operations. So where do we get this data from? Where is this data coming from? This data definitely has to come from some database servers or some external sources. Basically, the events happening in the real world would be captured by transaction processing systems, and they would get into RDBMS. And some of the events happening in real worlds, though data generated by those kind of systems which cannot be captured by RDBMS systems, they would be residing in some other unstructured file format, basically in text format or some other comma separated values, CSV files, whatever it is. So data basically needs to be brought into this HDFS environment of Hadoop, or this HDFS component of Hadoop, from the outside world, or from the world which is outside of Hadoop. So we need some kind of tools called, some of the tools are like Scoop and Flume, which is used to bring the data into Hadoop ecosystem. Scoop is a tool which actually is used to bring the data from the world of RDBMS, and Flume actually is used to bring streaming data, like unstructured or semi-structured data as it is being produced. For example, data from social networking sites like Twitter, like it doesn't find a perfect fit into RDBMS based systems, so it's a streaming data. It would be stored ideally as CSV files or text files or some other sequence files. And if you want to bring such kind of streaming data on the fly, you need to use a tool called Flume. And then you have data mining tools called some like Drill and Mahout, and there are like a ton of other tools for data integration and data mining, which you can look out in the Apache website. Like a lot of open source projects being contributed over there. And the right hand side, the yellow box over here is a set of management tools. Yeah, these are very, very important tools which is needed to monitor and manage the cluster. When we speak about distributed computing environment, it's pretty much understood that it's going to be a huge interconnection of multiple computers. And now managing all those computers is quite a task. So there are different kind of tools, like Ambari is one of the managing tools for managing and monitoring the Hadoop cluster. And Zookeeper is another kind of tool which helps in managing and monitoring. The basic functionality of Zookeeper is to ensure that all of those data nodes are synchronized in terms of clock synchronization. And Oozie actually is a workflow manager. So we shall discuss about Oozie in the subsequent slides. And just for time being, just understand that there could be like several kinds of jobs, hundreds of jobs being submitted. So Oozie is basically a workflow manager which helps you to design or decide. It's like a flowchart. It's like a flowchart design which helps you to decide in what sequence the jobs will have to be executed. So in a subsequent videos, we would be pretty much trying to learn what exactly Oozie is, how exactly Ambari and Zookeeper work, and some hands-on exercises with Scoop and Flume. So that's it for now, and hope you had a good time. Goodbye.